Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 2nd, 2026, just yesterday. It introduces an open-source multimodal model that utilizes a parallel orchestration framework to cut inference latency by up to 4.5 times compared to single-agent baselines. The paper is titled Kimi K2.5 Visual Agentic Intelligence. And as we'll see later, the implications for handling long-horizon tasks through parallel processing are quite significant. On Hugging Face, you can find Kimi K2.5 weights featuring 32 billion parameters. The page also includes usage examples and inference tools to help you get started. To see how this stacks up, Figure 1 compares the model against top-tier systems like GPT-5.2 and Claude Opus 4.5. The blue bars highlight Kimi K2.5, which achieves state-of-the-art performance across agents, coding, image, and video domains. In the agents section on the top left, it secures a notable lead on benchmarks like Humanities Last Exam and BrowseComp. Furthermore, looking at the video results in the bottom right, Kimi K2.5 surpasses the competition on Long Video Bench, validating its architectural improvements. Well, Figure 1 established the model's strength, and now Table 1 reveals the training recipe behind it. This experiment tests when to introduce visual data, comparing early injection against the standard late approach. Surprisingly, the top row demonstrates that adding vision tokens early at just a 10% ratio yields the highest scores across the board. For example, in the vision reasoning column, performance drops from 43.8 with early fusion down to 39.0 in the bottom row. This suggests that joint optimization from the start is more effective than adding vision as an afterthought. Okay, following that pre-training insight, Figure 2 tracks how the model improves during the reinforcement learning phase. These four charts display accuracy rising steadily as the training compute, or RL flops, increases across various vision benchmarks. For instance, in the top left, performance on MMMU Pro climbs significantly from the baseline. Similarly, the green plot for MathVision on the right shows a consistent upward trend. This confirms that even starting from a minimal zero vision foundation, where visual skills are initially activated via text-only proxies, scaling up reinforcement learning is enough to build robust visual capabilities. So, while Figure 2 focused on capability scaling, Figure 3 unveils the structural innovation, the agent swarm framework. On the left sits the orchestrator, a trainable model that manages the entire workflow. Rather than solving a complex problem linearly, look at the top row, where it dynamically spawns specialized subagents, such as an AI researcher or a web developer. The large middle section then illustrates the core advantage. The orchestrator assigns dozens of tasks, seen here as Task 1 through Task 100, to be executed in parallel. This distributed approach allows the system to handle massive, complex workloads without getting stuck in a long, single-file queue. Alright, Figure 3 outlined the swarm architecture, and now Table 4 puts it to the test with a comprehensive comparison against both proprietary and open-source giants. Starting with the reasoning and general section at the top, look at the HLE full with tools row. Kimi K2.5 scores 50.2, which actually outperforms Gemini 3 Pro in GPT 5.2. However, the Agentic section is where the swarm framework really shines. Notice the jump in BrowseComp. The standard model scores 60.6, but with Agent Swarm enabled, that surges to 78.4. Similarly, in the coding section, it achieves 76.8 on SWE Bench Verified, maintaining a strong competitive edge across these diverse tasks. Well, having seen the performance jump, Figure 8 now demonstrates the efficiency gains. This chart plots execution time against task difficulty. Notice how the red squares for the single agent skyrocket as the target score increases to 70%. By comparison, the blue circles for the agent swarm remain consistently low, barely rising even for complex goals. This results in the 4.5 times speedup shown on the right, confirming that parallel execution effectively prevents the bottlenecks typical of sequential models. Wrapping up, two takeaways stand out. The shift to parallel orchestration effectively solves critical latency bottlenecks, and joint text vision training creates a much stronger foundation for general intelligence. With these open source weights now available, the community can build directly on these scalable architectures. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.